Good afternoon, class. Here's exam 4, covering chapters 4 and 5 from section 4.4 optimization problems to 5.4 the substitution rule. We've done the first half, and here's the second half. We want to integrate, and notice when we have a fractional format, the very first step is to simplify if we can. If there's a common factor, we drop it. When we cannot, the denominator is a choice of u. In this case, u is 5 plus e to the power of t. The derivative is e to the power of t, which makes du e to the power of t dt. We're going to rewrite this by putting the dt at top, and therefore clearly you have the integral of du over u becomes a natural log of absolute value of u plus c. Replace the u, and because this is always positive, in fact it's larger than 5, you can drop the absolute value. ln of 5 plus e to the power of t plus a constant. What about this one? Can we simplify? Can we factor? The answer is no. How do we know that? I want to remind you of the quadratic formula. Ax squared plus bx plus c equal to 0. X is minus b plus minus a squared of b squared minus 4ac over 2a. And b squared minus 4ac is called the discriminant. It is called the discriminant because it gives you a lot of information. When it is positive, it gives us two distinct real solutions. When it's 0, it gives us one real solution, a rational solution. When it's negative, no real solutions, or two complex solutions, a plus minus bi. Furthermore, if b squared minus 4ac is a perfect square number, that means we can factor the quadratic expression. So having said that, can we factor this? Notice a equals 1, b equals 2, c equals negative 1. So b squared is 2 squared minus 4 times a, which is 1, times c, which is negative 1, gives us 4 and 4, 8. Is this a perfect square number? No, it cannot be factored. Therefore, the denominator is a choice of u. Notice if we differentiate, we get 2x plus 2. So du dx is 2x plus 2, and I can factor the 2 out. Therefore, du is the same thing times dx. We're going to rewrite the fraction such that dx is at top, always is at top. And we notice number 2 is missing here. As I mentioned before, you can solve for dx, or because this is a number, you can write this here, put it in, undo it with its reciprocal 1/2. Now the top is du, the bottom is u, and the 1/2 outside remains. This is just like this one, a natural log with the 1/2 in front. So half of ln of absolute value of u plus a constant. Replace the u, keep the absolute value because the expression can be positive or negative. Now, what if we have the reciprocal of this one? You have to divide using either long division or synthetic division. So that's the way you do it. But if we have the reciprocal of that one, in other words, you don't have to use the u substitution. So you make up two fractions, 5 divided by e to the power of t, or 5 e to the power of negative t. E to the power of t over e to the power of t is 1. This one, we take the integral and it's the same. We have to divide by negative 1 becomes negative, and this is t. So we get minus 5 e to the power minus t plus a constant. And that's the final answer. The integral of 5 plus 2 cosine theta d theta, notice the independent variable is theta, therefore 5 gives us 5 theta. Cosine, the derivative is negative, and the integral is positive sign, so therefore plus 2 sine theta and a constant. What happens that the integral involves exponentials? In that case, normally the exponent of e is the choice of u. If I differentiate, I get 5x to the power of 4. Therefore, du is 5x to the power of 4 dx. I'm going to rewrite this by moving x to the power of 4 next to dx, so it becomes clear everything is in order except number 5 is missing. So we have a choice of solving for dx, or simply put, because this is a number, we can put number 5 here, undo it by putting the reciprocal 1/5. Again, the product of the two numbers, and only numbers, must be 1. Therefore, we are dealing with 1/5, the integral of e to the power of u du. So the answer is 1/5, e to the power of u, and a constant. Reverse substitution results in 1/5, e to the power of x to the power of 5 minus 2, plus a constant. We are done. What happens when trigonometric functions are involved, more specifically sinusoidal functions? If the argument is a function of x rather than being x, t, or theta, it's a function of an independent variable, then the argument, in this case x squared, is a choice of u. The derivative is 2x, which makes du 2x dx. We move things around by moving x next to dx. So what is missing? 2. Again, 2 is a number. We can put the 2 and its reciprocal, 1/2. Again, please understand, inside or outside the integral sign makes no difference. The product must be 1. And we can only do these two numbers. So we have 1/2, the integral of sine u du. The derivative is positive, but the integral is negative cosine. So negative 1/2 cosine u and a constant. We're dealing with this, right? I replace the u with x squared. The final answer is negative 1/2 cosine of x squared plus a constant. What happens when we have both sine as well as cosine? Remember, the derivative of sine is cosine. The derivative of cosine is negative sine, and a negative number is not a big deal. We can always create one by putting negative 1 and its reciprocal. So when sine and cosine are involved, the one that has the exponent is a choice of u without the exponent. If both of them have exponents, then you have to use trigonometric identities to bring one of them down to exponent 1. Sine squared plus cosine squared equals 1 will normally do the job. Having said that, if the u is sine, the derivative is cosine, and the u is cosine x dx. So this is u squared, this is du. And so the answer is 1/3 u cubed plus a constant. You replace the u with sine, and you get 1/3 sine cubed x plus a constant. What if we have the integral of cosine to the power of 20x sine x dx? Well, cosine has the exponent. Then cosine is a choice of u. Its derivative is sine, negative sine x, which makes du negative sine x dx. So everything is there except the negative side, which means negative 1. So I can rewrite this with a negative sign next to it and negative outside. Remember, -1 and -1, the product is +1. So minus the integral of cosine to the power of 20x times minus sine x dx becomes minus the integral of u to the power of 20 du. And using the power rule, -1/21, u to the power of 21, and a constant. Replace the u with cosine, and the final answer is -1/21 cosine to the power of 21x plus a constant. What if the integral involves ln x? In that case, the choice of u is ln x. The derivative is 1/x, which makes the u 1/x dx or dx/x. To make sure we can see what we are dealing with and the reader can see it, so we are going to rewrite it as ln x to the second power times 1/x dx. Again, any format is fine. This is u squared. This is du. Power rule results in 1/3 u cubed plus a constant. Replace the u, we get 1/3 ln of x to the third power plus a constant. Please understand, ln x to the third power means ln x times ln x times ln x. Do not mix up this one with this one. Okay, this is the same as 3 ln x, okay? So you must put it in a parentheses and raise it to the power of 3. Two different things here. What if we have a fractional format? Let me erase my work. Notice the derivative of e to the power of x is e to the power of x. The derivative of e to the power minus x is itself times negative. In other words, if you choose u to be the denominator, its derivative is the numerator. So du is the numerator times dx. Let's rewrite it. So we have the integral of du over u. That's a simple case of a natural log. So ln of absolute value of u plus a constant, replace it, and you're done. Bear in mind, e to the power of x plus e to the power minus x is always positive. You can lose the absolute value if you like. Again, natural log is involved, therefore, that's a choice of you. If I want to differentiate du dx is 1/x plus 1 times 1. So du is 1/x plus 1 times dx. So let's rewrite it so it becomes clear. This is u, this is du, and what are the new limits? We are going to write them. So I'm going to find the new limits. Before that, of course, this is a simple case of power rule, and therefore it's 1/2 u squared. We have to figure out the new limits. So I'm going to erase my work first, and then If I plug in 0 here, I get ln of 1, which is 0. If I plug in 1 here, I get ln of 2. So 1/2, plug in ln 2, quantity squared, and of course 0 doesn't do anything, it gives you 0. 1/2 ln 2 to the second power is an exact answer. And we are done. A bacterial colony increases at the rate of R of t equals 2.2 e to the power 0.4 t bacteria per hour. If the initial population is 800, find the population after 12 hours. Bear in mind, this is the rate, this is the derivative of a function. So if this represents the amount of increase as a rate, then let's say capital R of t represents the population, and this is capital R prime of t was lowercase r of t. This is the initial value. So we write capital R of t represents the population. Capital R prime is lowercase r of t represents the growth rate. And the initial value R of 0 is 800. This is understanding the problem. We have two ways to handle this. We can find the accumulated change, the definite integral, and find how much increase happens over the course of 12 hours, or find the function. So we're going to do both. The accumulated change or the net change theorem indicates that the population over the course of 12 hours follows the integral of 0 to 12 lowercase r of t dt. So let's replace it. Because it's exponential, the derivative and the integral are the same. In the case of integration, we're going to divide by k, see 1 over k to the power of kx. We're going to divide by 0.4. So we get 2.2 over 0.4 e to the power of 0.4 t, evaluated from 0 to 12. This is 22 over 4, 11 halves, 5.5, or 5.5. We can take this out and plug in 12 minus plug in 0. Of course, this is 1, and this is 0, my apologies, and e to the power of 0 is 1. And this is 4.8. So you have to put it into the calculator, and we go with a couple of decimals because this represents the number of bacteria. We're going to round it to the nearest whole number, and because next to it is number 8, it goes up to 663. Now the initial population is 800, so we need to add them up. This represents the amount of increase. This represents the total population after 12 hours. And that's fine. The second method is to find this function. And to find this function, we are going to integrate this. And capital R of t is the integral of 2.2 e to the power of 0.4 t dt. And you know this integral gives you this one for definite integral. For indefinite integral, same thing plus a constant. Now, can we find the constant? R of 0 is 800. Replace the t with 800, R of t with t with 0, R of t with 800. So e to the power of 0 is 1. This is 5.5 plus what number? We get 800, 794.5. And that's the function. So what we have here is the general solution. With the help of an initial value, we get one solution. It's an initial value problem. And after 12 hours, replace the t with 12, it will give you the same answer. The advantage of this is if we are interested in finding the population not only after 12 hours, but also after 10 hours, 15 hours, 20 hours, just plug it in here. Whereas this methodology, you have to calculate it again. For example, after 20 hours, you got to go with 0 to 20. So you don't want to repeat that. You want to do that. But if it's only one part, either way is fine. Breathing. We can model the rate of airflow into the lungs by the function f of t equals 1/2 sine of 2 power 5 times t liters per second, where t is the time in seconds. Find the total amount of air inhaled in one cycle, known as the tidal volume, if the cycle lasts 5 seconds. Obviously, if in and out takes 5 seconds, inhaling takes only half of that. So the time for inhalation is half of the cycle. That means 5 half seconds. Therefore, the total amount of the air inhaled is the integral of 0 to 5 halves f of t dt, or the integral of 0 to 5 halves 1/2 sine of 2 power 5 t dt. Again, I'm just putting this, and on purpose, the number 1/2 in front, I put it in a different color because for me to integrate this, I'm going to take the 1/2 out. To make it easier to do. But anyways, what is u? What is du? Because this is not t, this is a function of t, then the argument of sine 2 power 5 times t is a choice of u. The derivative is simply 2 power 5, which makes du 2 power 5 dt. So now that I want to deal with this, I'm going to rewrite it. First of all, I'm going to put the 1/2 out. Secondly, I have sine 2 power 5 t. Thirdly, I have dt, and 2 power 5 is missing. Bear in mind, 2 power 5 is a number. Again, you could solve for dt, as many takes to, or simply put 2 power 5, put it in, it's reciprocal. 5 over 2 pi outside. Again, it can be done because it is a number. So you're dealing with sine u du. And what is this one? 5 over 4 pi. What are the new limits? Let's find them. If I plug in 0 here, I get 2 power 5 times 0, which is 0. If I put 5 halves here, I get 2 pi over 5 times 5 halves, which is pi. So the integral of sine is negative cosine u. So we're going to write 5 over 4 pi, negative cosine u from 0 to pi. In other words, this is 0. This is pi. And so let's take the negative sign out. Let's plug in pi and 0. As you know, we get minus 5 over 4 pi because we took care of the sign. Cosine pi minus cosine of 0. Cosine pi, negative 1. Minus cosine 0 is positive 1. Minus 1 is negative 2 times negative 5, we get minus 10, plus 10 over 4 pi, or 5 over 2 pi. This is exact, roughly 0.796. And if you go, you choose the number of decimals as they ask you. For example, 0.80. Because this is liters per second, then this must be in liters. So you want to be careful with that to answer it properly. We want to evaluate this integral. It's pretty straightforward. Please understand dt indicates that t is the independent variable. So 1 results in t. Cosine the derivative is negative, but the integral is positive sine t. The integral of cosine is positive. So we are going to evaluate this expression from 0 to power 2. And this is the only calculus step. So we plug in power 2, we get power 2 plus sine of power 2 minus, we plug in 0. And when we plug in 0, 0 sine 0, this is 0, everybody. And therefore the entire thing is 0. Now what is sine of power 2 is 1. And this is an exact answer. Power 2 plus 1. That's an exact answer. And what about this one? The integral of 1 to 4, 5x squared of x plus 3 squared of x dx. First, square root of x, we change it to x to the power of 1/2. This has exponent 1. They add up. We get 5x to the power of 3/2. The second piece is simply 3x to the power of 1/2. This one, 5 over 3/2 plus 1x to the power of 3/2 plus 1. This one, 3 over 1/2 plus 1x to the power of 1/2 plus 1. And evaluate it from 1 to 4. And believe it or not, this is the only calculus step. Everything else was algebra. Everything from here on is algebra. Plug in number 4 and plug in number 1. Before we do that, we notice this is 5/2. 5 divided by that is 2. This is 3/2. And this one is also 2. Now we're going to put in number 4 minus, we're going to put in number 1. So we are going to evaluate. First, let's just get rid of this. It's 1, and this entire thing is 4. Then 4 to the power of 5/2 means square root of 4. 2 to the power of 5 is 32. 2 times 32, 64. 4 to the power of 3/2, 2 cubed, 8. 2 times 8 is 16. Meaning, this is 2 times 32, 64, plus 2 times 8, 16, minus 4. 64 minus 4 is 60, and 16 is 76. And that's the final answer, everybody.